Hello and welcome to the workshop for modeling your plant. This is the workshop that we usually conduct together with our clients on site, and it usually takes 2 days to complete. We go through the same workshop whether we're setting up the Advanced Process Optimizer, APO, or the Intelligent Health Monitor, IHM. And these are the steps that we go through. First, we discuss the goal for optimization, and that step is only relevant for the APO product. Next, we select all the tags that we want to look at from the plant. We define the parameters of those tags. We export the historical data over the past months or years of all the tags that we've selected. We discuss the IT requirements so that we can install the software and run the models in real time. And lastly, we summarize the workshop and discuss the next step afterwards. So first of all, we go through the goal for optimization, and this is only relevant for the APO product. As APO is concerned with optimizing some key performance indicator, we need to decide what we are going to optimize. And the sequence of steps that's going to be executed over the long term when the APO product is in use is that we measure quantities in the process, we compute the mathematical model, come up with suggestions, then a human operator looks at those suggestions and makes any changes that may or may not be required, and as a result, you experience the improvement of the key performance indicator you want to optimize. That KPI that's being optimized has to be some sort of numerical value, and it could be a physical quantity such as efficiency or yield, or it could be a financial quantity such as profit. That is what we have to decide first. What is it that you will want to maximize? After we know the idea of what we want to maximize, there comes the task of spelling it out, how we're going to actually compute that value. So most of our clients choose financial profit as the KPI to maximize, and of course, profit is the revenue minus the cost. Usually we have a number of revenue items and a number of cost items, and they typically involve the multiplication of some sort of physical volume by the financial price. The example that you see in the slide in front of you is that I have two lines here, one revenue item, one cost item. Revenue item is the megawatts per hour produced power by a power generation plant multiplied by the price in dollars per kilowatt. And as a cost item, I have the tons per hour of coal that I'm burning in the power plant multiplied by, let's say, the price in dollars per kilograms of that coal. Now, those four items, the power produced, the coal burned, and the two prices, these are four quantities that, of course, change over time. None of them are constants, so all four of them will have to be tags that we incorporate in our model. But we note, for instance, that while power is in megawatts, the price for that power is in kilowatts. So we're going to have to convert kilowatts to megawatts in order to be able to correctly multiply those two quantities, and that's what the factor is for. The same thing occurs with the cost item, where we have to convert kilograms to tons. And so you see that the goal function is being specified in the software is in terms of a number of terms that are being added to each other that involve three elements each, a factor and two tags that are multiplied by each other. And of course, the fact that the first line is a revenue is indicated by the plus sign, and the fact that the second line is a cost is indicated by the minus sign. So if I add them together, it really does mean the profitability of that plant, and that is what is being maximized, and therefore I will be aiming at maximizing this profit. Whatever quantity you choose to maximize, this is the form in which you want to formulate how to compute it. So in order to get closer to it, we ask ourselves the following questions. What is the goal? For example, financial profitability. Where are the system boundaries? So what are the costs and the revenues that I'm willing to consider? So for instance, in the operations of a power plant, of course, paying salaries and wages for employees is a cost, but that is not something that's going to be accessible to a real-time process optimization algorithm. So we do not want to consider such sources of cost or such sources of revenue in our optimization. The only sources of revenue and cost that we want to consider are elements that we can actually have some sort of influence over. Thirdly, what tags do we need to compute the goal? In the example we looked at before, of course, we need the amount of power produced and the amount of coal put in, but we also need the financial prices of both. So there are already 4 tags that we needed in order to compute the goal function. Next, we need to discover what these tags are called. Usually in the control system or archive system, historian, these tags have very specific alphanumeric names that we have to discover to come up with an actual precise list of the tags that we need in order to compute the goal function. Supposing that we want to study finances, the question is, are the prices variable? And if so, where are they? If a price were constant and never changing, of course we can incorporate the price in the factor and have it simply be a constant. If the price is variable, that variable must be a tag that we can pull from the control system or archive system. And that may require, in some cases, for these tags to be specially found or created. So we need to watch out that if we have some things that vary over time but are difficult to access, that these be made available. That was for the APO product, and now we proceed in generality for the selection of all the tags that we need to model our plant. So the task is to collect all the tags that we need to model the plant accurately. There are 2 basic ways of going about this. One method is to start with an empty list and add every tag that we believe to be reasonable and important for modeling the plant. The other method would be to start with a list of all available tags and delete the ones that we consider to be irrelevant. Now, the first method, by which we start with the empty list and collect everything we think is reasonable, is, in our experience, the better method. And the simple reason for that is that the elimination method usually results in very, very long lists of tags, including a large number that we do not need. If you are ever in any doubt whether to include a tag or not to include it, it is better to include it and therefore to err on the side of having a longer list rather than a shorter list. In order to help you in this process, here are some of the questions you can ask yourself to include these tags in your list. What are the tags that are often changed by the operators? These are the set points of your process over which the operators have actual influence that are usually included in the interface of your control system. Which are the tags that may be changed by the operators? These are not the same necessarily that are often changed by the operators. For instance, these are usually controlled variables that the operator can disconnect from the advanced process control and modify manually, but are usually under the influence of advanced process control. Next, we might need any measure of supply and demand, financial prices for either the raw materials that go into the plant or the prices for the products that leave the plant. Oftentimes, the weather and some external world influences, maybe the temperature of the cooling water source, or the amount of rainfall, the outside air temperature, such influences may or may not be important for your plant, and they might have to be included. Which tags might show some important properties of the process? For instance, any boundary conditions regarding safety or some other restrictions that the process has to obey perhaps some specification criteria of the end user that the product must fulfill. What tags might indicate the quality or the purity or other important characteristics of your end product? And of course, lastly, what we've already been through, what are the tags that are needed to compute your goal function? So the task would be now to go through these questions carefully, one by one, and to ask ourselves, which are the tags that we need to answer all of these questions? What are the important tags in the process that describe it from beginning to end? Having obtained a list of all of these tags, we want to define the parameters for each of these tags, and these are the kind of parameters that we want to collect. So first of all, every tag has a name. Now, there are several types of name for each tag. So first of all, the tag has an alphanumeric nomenclature by which it is called in the control system or the historian. But it usually also comes with a human-readable text description of what it is and where it is. Secondly, there is a source for this tag, which is the name that it takes in the OPC server, OPC being the industry standard data exchange protocol by which any software, such as ours, might read the real-time value of that tag from either the control or archive systems. Thirdly, every tag has some sort of physical unit, whether it be kilograms, percent, or dollars, and that has to be specified. Fourthly, there's an allowed range of values. So every tag has a minimum and maximum allowed value to it, and the reason why this is important to us is that if we see a value that is below the minimum or above the maximum, we can identify that measurement as being not allowed, not physical, impossible, or one of those. In other words, we will ignore any measurements that are outside of that range of values. Next, every measurement is somewhat uncertain. There is no physical measurement that can be always very precise, and we want to discover what is that uncertainty and specify it. This is important because uncertainty in measurements leads to uncertainty in computation, and therefore our modeling process and the use of those models are under the influence of uncertainty that are coming from the actual measurements. Next, every tag can be either a control point, a set point of the process, a pure measure which adjusts itself to the outside world, or it could be a boundary condition, namely a value over which we have no control whatsoever. And lastly, we may wish to set some fixed and standard alarm limits so that if the process gets out of control, the software is able to send us an alarm message. And we will go through a couple of these concepts in a little bit more detail in the next slides. Here, for instance, you see a diagram where the value of a particular tag is the vertical axis and the timeline is the horizontal axis. We would normally want that the measurement be in the middle, in the normal green region. And in order to define where that green region is, we have a low green and a high green value that defines it. Outside of the normal green region, we have three colored regions that indicate some form of abnormality. Just outside the green range is the yellow range, which is dangerous. Outside the yellow range is the orange range, which is critical. And outside the orange range is the red range, which indicates an actual failure, a trip of the machinery or a breakdown, some kind of unplanned downtime of the machine. And outside of the red area is the region that is explicitly disallowed. This is a region which should never occur at all. The beginning and end of the gray region is the minimum and maximum values that I spoke about before, which must never occur. And within that allowed range, we have these various colored regions, which we can specify if we want, but we do not have to specify. All these colored regions will do is release alarms. The uncertainty of a tag merits some more discussion. First of all, every physical sensor that is installed in a process has a tolerance in it. And the manufacturer will tell you what that tolerance is, but that tolerance is usually very, very small. And so I discourage you from trying to discover what that tolerance is. It is, frankly, a waste of time in these projects because the uncertainty is dominated by other factors. After you have measured the value with the sensor, which is usually an analog electrical signal coming out of the sensor, that is converted into a digital value, and that conversion has a round-off error, in other words, an uncertainty. That digital value arrives at the control system and is again subject to a round-off error. The control system's value is backed up by the archive system or the historian, and those values are usually saved only if the value differs from the last value saved in the historian by a certain amount, and that certain amount is called compression factor. Depending on what you have set the compression factor to be for the particular tag, that is usually the dominant factor in this, and is usually quite large. On top of that, every measurement has a cadence. In other words, you don't measure the process every single moment, but you might measure it once a second or once a minute, and therefore what happens from minute to minute is never seen by the archive system, and therefore that again introduces a measurement of uncertainty. Therefore, the entire measurement chain has a significant uncertainty attached to it, which is usually far, far greater than the sensor's original tolerance. Usually, the entire chain's uncertainty is completely dominated by the compression factor in the historian. Therefore, I advise all of my clients to simply look at the archive system or the historian and to look at what the compression factor has been set to, and that value is a very, very good indicator of the total uncertainty of the measurement. You don't have to make this into a very long discussion. Just extract the compression factor from the historian, and that will be the uncertainty of your tag. Next, we have to discuss over which tags we have control. And there are three possible versions of control. So every tag will be categorized into one of these three types. The first type is that we have control over it, which means that the operator in the control room can manually enter a new value for that tag, and that value will then be realized in the physical process. We know that usually under the name set point. So if we have complete control over it, it's a set point. The next category is the opposite of we have no control over it whatsoever. These are things like the temperature of the outside air or the quality of the raw materials that some supplier sends to us. This is a value that the operator in the control room has no control over at all, not even a little bit. The third category is everything in between. The operator cannot set the value for that tag, neither does the world set the value for that tag, but rather the value emerges as a reaction to the system and partly as a reaction to the set points that the operator can control. So here are some examples. A direct set point where the operator changes a process temperature, that is a controlled variable. The outside air temperature is a non-controllable variable. And a vibration in the process is neither controlled by the operator nor is it determined by the world, but rather the vibration in the process is a reaction to some of the things such as temperature or flow rate that the operator does control via a set point, so those are semi-controllable. When deciding whether you have some control, full control, or no control over a particular tag, please keep in mind that the focus here lies on the operator in the control room. We are not concerned with the corporation, the management, the division inside the company, or whether it's possible in principle. We are concerned with what the operator in the control room can actually practically do. And that will decide how much control we have over each tag. If we're setting up the IHM product, we have one more decision to make, and namely, which of the tags are going to get alarms. Now, the IHM product alarms you when the physical measurement is significantly different from the mathematical model for that tag, where the model, of course, encapsulates the healthy behavior of the equipment that's measured by that tag, and therefore if there is a difference between the measurement and the model, the definition of health currently doesn't hold, so we're assuming that the machine is under some form of sickness, and therefore an alarm is released. So we're effectively asking, for which tags would you like alarms if that machine is no longer in good working order? And so it must be those tags that are somehow indicative of machine health and that would be useful in order to plan some kind of maintenance activity for that piece of equipment. The next question is to decide how to train these models. Because the models are supposed to encapsulate the idea of healthy behavior, we have to decide at which period in history the equipment was in fact healthy. So you will need to decide on times and dates and time periods for which you know that the equipment was healthy in the past, and then the models will be trained on that historical time period. As a result, the model then can encapsulate healthy behavior, accurately detect machine sickness, and because of the tags you've chosen, will be able to send you alarms that will be useful in your use to plan maintenance activities for those tags, respectively for those machines. What we see here is a file in Microsoft Excel which combines all of the parameters that I've been talking about and displays them in a tabular format. This is the format that you want to choose to list your tags and their parameters in, and we will supply you with this Microsoft Excel document to start with to discover your tags and to enter their parameters. You'll want to save this as a tab delimited ASCII text file after you're done with it, but the Microsoft Excel environment is just simply convenient for listing all the information. So in the first column, you list your tag name, which is the alphanumerical name that you would give it in the control system. The second column then contains the name in the OPC server, and this may or may not need to contain additional OPC item names in order to be able to identify where in the OPC server this value is located. In the next two columns, you can supply a short and a longer description that would be human readable of whatever that tag is about. The next column would give the physical units of that tag, then the minimum and maximum as actual numbers, given in the same units as the tag itself, and next follows the 2 green, 2 yellow, and 2 orange limits that I've discussed in the presentation, which are all optional. By default, we generally leave them empty because their only function is to generate static alarms. The delta in this column is the uncertainty due to the entire measurement chain of that tag, and this is given as a number in the same physical units as the tag is measured in. Whether or not this tag is to receive an IHM dynamic limit model is indicated here in this column limit by telling it to be either true or false. If it's true, that tag will get a mathematical model for its dynamic limit. If it's false, it will not. Then the control column classifies each tag into the three categories discussed, namely, is it a set point and therefore directly controllable by the operator? Is it the opposite and the operator has no control over it whatsoever? Or is it in the middle where the operator has some amount of control but not direct control over it? And these are the terms we want to use. If we have a set point, it's called controllable. If it emerges, then it is semi-controllable. And if it is a value of the outside world, it is uncontrollable. The last column in this file is to distinguish whether or not that tag is accessible for reading via an OPC server or whether this value is a manual input. Now, we either write OPC or manual in this column, but I would encourage you to include only OPC items. Only in very exceptional circumstances should there be a manual input tag included in these lists, simply because of the amount of effort and the potential for error that's involved in including a tag that requires continuous editing by a human user. So after having filled in this form here in, for example, Microsoft Excel, you would want to copy and paste this into a tab-delimited text file, and that is something that you can then import into the software. That concludes deciding the parameters for all these tags, and next is to export the historical data for all of these tags. We have to decide a few simple concepts here, namely what time period do we look at for the history. Now, oftentimes the weather is an important influence on our process, which means that the time period to be extracted for history should include summer and winter interactions, so I typically recommend that one extract at least one past year to get the full range of seasonality into the dataset. For maintenance questions that regard machinery that is not subject to the weather, you may get away with choosing a time period that is less than 1 year, but the dataset should include several months worth of good data to train from. Otherwise, the model may not be the best quality. The second question to decide is what time cadence to choose for the dataset. That means, do we take a new point every minute, every 5 minutes, every hour, or every second? That question is usually determined by the physics underlying the process. So it's an engineering question. What is the time scale of the process that we're looking at? So if we're optimizing a chemical process that takes place over the scale of many minutes, then it might be enough to sample the process every 5 minutes or every 1 minute. If we're looking at damages to machinery that might occur within the space of a few minutes, then we might have to sample that every 60 seconds or every 30 seconds. So that question is answered essentially by the process speed or the damage mechanism speed that we're looking at here. Having answered these two questions and being in possession of a list of tags that we're looking for, we need to write some sort of export script. Whatever your historian system is or your control system that holds these historical data, we need to extract it to a CSV file. The first column in that CSV file will be the timestamp, and every other column in that CSV file will be the actual measurement value of each tag on our tag list. And of course, the order of columns in the CSV file for the data should be the same order as the tags in the list of tags. Now, one important format requirement is that the timestamp should be in one of these two formats that's cited here. In other words, the normal international time format that starts with day, month, year, and then the time of day, or in the ISO format, which is year-month-day, and then the time. In both of these time formats, the .xxx, which indicates milliseconds, is optional. The rest of the timestamp must be according to this format. This is the example text file that includes the actual data. I've opened this up in Notepad++, which is a standard text editor, and as you can see, it's a semicolon delimited text file that includes first a timestamp and then the actual floating point numbers. In this particular file, the timestamp is of the day, month, year, space, hour, minute, second format. It doesn't have the milliseconds, which are optional anyway, but the first column is always the timestamp, and then following are the values in the same order as the tags were on the tag list. And that's the kind of format of a file you would like to export from your historian. Algorithmica will supply you with this file as a sample so that you can work with it in order to extract your file. Having concluded with both of the tag list and the data list, finally we discuss the IT requirements for installing the software. The software is such that you have existing data sources and an OPC server that can supply the values of that data. Everything in the green box is the software supplied by Algorithmica, which has an OPC client that reads that data from your OPC server, stores that data in a PostgreSQL database. Then a number of mathematical methods from machine learning, optimization, and predictive analytics operate upon that data and write their results back to that database. These results can be the modeling process itself, or it can be using the models in order to determine what one should do or in order to release alarms. All of these functions obtain their data from the database and write their results back to the database. And lastly, there is a user interface that runs on the same computer as well, and this is accessible via a browser. So any computer that is connected to the network that this software runs on can then view the user interface via any standard web browser. In order to install the software, all you require is a server that runs Windows 64-bit operating system. The server needs to have access to the OPC server in order to read values, and it also has to have access from the Office network so that the users can open a web browser and look at the user interface. So some firewalls might have to be configured in order to allow access both from the OPC server and from the Office network. Now, for the software to be installed correctly, Algorithmica needs an account on that computer with administrative privileges so that the software can be installed. Algorithmica also needs to have remote access of some type to that server so that we can perform maintenance activities and all form of help and service activities to help you achieve the full potential of the modeling software. This remote access does not necessarily have to be active at all times. It could be made active on demand whenever it is desired that Algorithmica perform some service for you. Finally, we summarize and discuss next steps. We essentially check whether we have gotten everything we needed. Have we discussed the goal function and made the goal very precise and computable using the actual tags? Do we have a list of all tags that we need to characterize the process, and have we collected its full metadata? Have we collected the entire historical data set? If we're in possession of a precise goal function formulation, a full list of tags, and the historical data, then we have done our job in this workshop. The discussion relating to these items and the actual doing of the work in our experience usually occupies about 2 days of work. Lastly, what are the next steps? Now that the data has been set up, we would model all this, come up with the mathematical models, and report upon their accuracy. Next, we would set up the server with all the requirements discussed, install the software, and together look at these models to determine how suitable they are for actual use. Not in all cases would the models be immediately useful, but we sometimes discover that some of the information collected during this workshop is either incomplete or somewhat incorrect, and that is discovered during the process of actually looking at the outcome of these models and seeing that this or that fine detail needs some adjusting. And that's what the fine-tuning process is for. That usually needs a couple of days on site. Finally, having fine-tuned the models, the software can go into real live operation and deliver you the business value that you were after. Thank you very much for your attention.